This is the fourth and final section of the methods in differential equations chapter, and here we're going to be looking at boundary conditions. Now, boundary conditions are basically values of x and y and the first derivative to allow us to work out the value of the arbitrary constants a and b. Okay, so let's just write this down. So boundary conditions are values of x, y and dy dx, if those are the letters that we're using. Values of x, y and dy dx that allow us to calculate the value or values of the arbitrary, let's spell it correctly, constants, and normally those constants are like a and b. Okay, now I said here about if those are the letters we're using, yeah. Now we could, for example, have a second order differential equation which is something like this, dx squared over dt squared, so some values there, dx over dt plus c, and this would be t, equals some sort of function of t, yeah, in which case we would be told what x is, or what t is like our x, we'll be told what x is, that will be like our value of y, and then we'll be told the value of dx dt. Actually, this wouldn't be ct, it would be cx, like that. Yeah, so you'll be given a value for x, a value for y, a value of the first derivative. Quite often there's all zero, and then that will allow us then to work out what our arbitrary constants are. So we might have an equation which is something like this. So let's just make something up. And let's say we've got something like this is our particular integral. Okay, so that will be our general solution with values of x, y and dy dx, which does mean we'd have to work out what dy dx is here. So we'd have to differentiate this, whatever we've got in our question. So, you know, in this particular example, I would get something like this. So I'm just, you know, it's just a made up question. And, you know, I'll have the value of dy dx and I'll make it equal to this. I'll put x equals whatever, y equals 0, whatever, into this, and I'll get two equations which I can then use to find my values of a and b, those arbitrary constants. Okay, so find in terms of x, given that we have this differential equation here and we're given these bits of information. So these are the boundary conditions. So all of these conditions are true together at the same time. So when dy dx is 0, y is 0, and x is also 0. So we're going to start by finding the complementary function. So we solve this as normal to get a general solution. Then we're going to substitute in our dy dx equals 0 and x and y 0 to find the particular solution. So for the complementary function, I'm going to get the auxiliary equation with a equal to 1, b equal to 0 and c equals to -1. So that will give me m squared minus 1 equals 0. So m squared equals 1, which means that m is either 1 or m is minus 1. When I have two real solutions, my general solution is of this form, like this. Alpha equals 1, beta equals -1. So I have y equals a e to the x plus b e to the negative x. So this part here is my complementary function. Yeah. So the next thing I need to do is to find my particular integral, pi. So that's what I'm going to do now. Now, because my f of x is in this form, 2e to the x, you may want to try a particular integral of this form, y equals lambda e to the x. But if we have a look at the form of our particular integral, this occurs, a term like this occurs in our complementary function. Something times by e to the x, we've got something like that. A constant times by e to the x, a constant times by e to the x. So we can't use that. We've actually got to times it by x and use this particular integral. So y equals lambda x to the ex. So that's what we have for y. So now we'll find dy dx. So we'll use the product rule where this is u and this is v, and we'll have lambda x e to the x, that's our u v dash, plus lambda e to the x, so that's our v and u dash. We'll differentiate again like this. Now we need to differentiate this, but notice that's basically exactly the same as this. So this differentiated is going to be all of this, yeah, because we've done it already. So to save ourselves a bit of time, and we'll write lambda x e to the x plus lambda e to the x. Yeah, that's basically just using the product rule on this. Yeah, but seeing as we've already worked that out once, we'll just use it again. And then I just need to add this differentiated, which is going to be lambda e to the x. Oops, in black. That's lambda e to the x. That can be simplified. I'll have lambda x e to the x plus 2 lambda e to the x. So I'm now ready to write my, or to work out the value of lambda in my particular integral. So I know that I need the second derivative here minus y. So I'll minus this, and that equals 2e to the x. So lambda x e to the x plus 2 lambda e to the x, that's d squared y over dx squared, minus y, so minus lambda x e to the x, just put the x in, lambda x e to the x, that equals 2e to the x. Now comparing coefficients, got 2 lambda there, and I've got 2 there. I will have 2 lambda equals 2, which means that lambda equals 1. So my particular integral, when I replace lambda with 1, is going to be x e to the x. So that is our particular integral. Now we'll write the general solution, which is our complementary function plus our particular integral. So that will be y equals a e to the x plus b e to the minus x plus x e to the x. Now we're going to find our particular solution, and we'll do that by doing the substitution. Now we're told that dy dx equals 0, so we're going to differentiate this and make it equal to 0. So when we differentiate that, we'll have a e to the x minus b e to the minus x. Then we'll use the product rule on this, u and v, and that will give me plus x e to the x plus e to the x, and that equals 0. Now we're going to substitute in x equal to 0 into this as well, yeah, because all these conditions are all satisfied at the same time. So all of these x's here will become 0. So this first term just becomes a when x is 0. The second term just becomes b when x is 0. Obviously this term will disappear and I'm left with plus 1 here. Okay, so I've got basically a minus b equals negative 1 as one of my equations. I can substitute x equals 0 and y equals 0 into this to get another equation, because I've got two unknowns. So let's just draw an arrow like this just to show that it's x equals 0, y equals 0 that I'm substituting into the original equation. So that gives me 0 equals, now again, what's going to happen to all of these terms where x is 0, so that'll just leave me with a as the first term. The second term is just going to be b, and then the third term here just disappears because x is 0, so it doesn't matter what e to the power 0 is, x is going to make it disappear. So I've now got a plus b equals 0. Okay, so it's just about solving simultaneously. So for example, I could say here that a equals negative b. I could then substitute that into this equation here to give me negative 2b equals negative 1. That will give me b equals a half, and then going back to this equation, it means that a equals negative a half. So a equals negative a half. So now our particular solution is going to be this, but with negative a half put here and half put here. So final solution, y equals negative a half e to the x plus half e to the minus x plus x e to the x. So let's just highlight that. That is our particular solution there. Okay, given that a particular integral is of the form lambda sine 2t, find the solution of the differential equation for which x equals 0 and dx dt is 1 when t is 0. So first of all, these are our boundary conditions here. So first of all, we start with the complementary function with a equal to 1, b equal to 0, and c equal to 1. So this is slightly different to what we've seen. All of the differential equations we've done so far have all been like dy dx, yeah, and d squared y over dx squared. That's why I sort of paused a bit, because this is just using different letters. So dx squared over dt squared. So it's like this really, dx dt plus cx equals a function of t. So I'm guessing this differential equation represents something which is a function of time, beginning to move into the next chapter, which is about applications and modelling with these differential equations. Anyway, so our auxiliary equation is going to be m squared plus 1 equals 0. So that's going to be m squared equals -1. So we're going to have complex solutions or imaginary solutions. So we would have plus the square root of -1 minus the square root of -1. What's that negative? And we know the negative of or the square root of -1 is I. So we end up with I and minus I as our roots. Just as a reminder, when we have complex roots of the form p plus or minus qi, then we get a complementary function which is, or a general solution of y equals e to the px times by a cos qx plus b sine qx. Yeah, now in this case p is 0. P is 0. Okay, so that's what we have in our case here. P is 0 and Q is 1. Now if Q is 0, then all of that disappears. We don't need to write it. So we can write our complementary function as y equals a cos x, because Q is 1, plus b sine x. So we'll just highlight that there. That is our complementary function. And I'm just going to correct this. So used to writing x, it should be t. Yeah, because this is a function of t. So make sure you don't make the same mistake that I did. Right, so I'll just move this out of the way. Put this over here. Because now we are going to find the particular integral. Now we've already been given the form that the particular integral is in, lambda sine 2t. So we can go straight away and write down that x equals lambda 2t. Now we need to be careful. We're so used to writing y equals, you might be tempted to write y equals lambda sine 2t, but in this case it's x. So x equals lambda sine 2t. So that's been given to us, okay, and we'd probably get that anyway, because when we look at what f of t is and we look at the table, we know that it would be like of this form, but there'd be a cos 2t there as well. But since it's been given, we don't need to worry about that. So we differentiate, so we want to make sure we get the right letters. So that'd be dx dt. So if we differentiate this, we'll get 2 lambda cos 2t. And then when we differentiate again, okay, there it's going to become negative. So we'll have negative 4 lambda sine 2t. We'll now substitute these into the differential equation. So we've got the second derivative, and let's carry that on up here. So the second derivative, negative 4 lambda sine 2t plus x So x is this lambda sine 2t equals 3 sine 2t. So we'll compare coefficients. So over here I've got negative 4 plus lambda, 3 there. So that will give me negative 3 lambda equals 3, which gives me lambda equal to negative 1. So now I have my particular integral as negative sine 2t. So this bit here is my particular integral. So now I can write that the general solution is going to be my complementary function y equals a cos t plus b sine t plus my particular integral there. That's general solution. I now want to find the particular solution, so I can do that by substituting in dy dx equals, or sorry, dx dt equals 1, and that means I should really be writing not y equals here, but x equals. So I've got a couple of corrections to do here. This should be x, this should be x. There we go, so that's more like it. So hope that didn't cause you too much confusion. Should be using x and t. So particular solution now that I've corrected those letters. So let's find first of all dx dt, because I know dx dt equals 1. So dx dt is going to be negative a sine t plus b cos t minus 2 cos 2t, that equals 1 when t is 0. So let's think about what happens when t is 0. So when t is 0 there, sine 0 is 0, so that's gone. So we don't need to worry about that. Cos 0 is 1, so we have b. And cos, well, that's 2 times 0, that's 1 again. So I'll basically get negative 2. So b minus 2 equals 1. That should be very easy. B equals 3. So I've got my value of b. Now we'll use our x equals 0, t equals 0 plugged into our equation. So I'll just write down here at x equals 0, t equals 0, which we are substituting into this equation here. That will give us a cos 0 plus b sine 0 minus sine 2 times 0, I don't really need to write all of this out, equals 0. So what does that give us? That will give us a from the first term. That will disappear. This will disappear. So that just gives me that a equals 0. So that's possible. So now I'm ready to write my particular solution with a equals 0 and b equals 3. So I will have x equals, now if a is 0, this is gone. And then plus, or just 3 sine t minus sine 2t. So there we go. here's our particular solution. So that's probably the last bit of the question, I think, was to actually calculate what the particular solution was. Okay, you should now be able to do exercise 7D on pages 164 to 165. So just remember that when we want to find we start with our general solution, which we should know how to do. When we've got our general solution, we substitute in, so sub in our boundary conditions, and these are normally things like x equals something, y equals something, or it could be t, and dy dx equals something. So you're told something like this. Just watch out if the letters are different. So the example we just did, it was t x and dx dt. Yeah, it's easy to fall back into just using x and y like I did. But anyway, once you substitute in your boundary conditions, you then get our particular solution, where we're able to work out the values of our arbitrary constants a and b.